Hi guys. Okay, so in this video, we are going to look at nomenclature, which is writing the formula and the names of ionic and the covalent compounds. We are going to look at the group number and the ions associated with the group numbers, and the monoatomic ions, the naming and writing the formula, polyatomic ions, naming and writing the formula, variable charges on some of the elements, and then the hydrates and covalent compounds, how to name them, and the acids. Okay, so all the names and the associated formulas of the compounds will be covered in this video. And here, as you can see on the screen, is a review from one of our previous lectures, which was where we said that group number and how the charges are related. So group 1A, all the elements in group 1A will have +1 charge. Elements in group 2A, +2 charge. 3A, +3 charge, that is for aluminum, and the others are variable. Group 4A is a mixture of metals and non-metals, so therefore the charges, or this is going to vary. Then comes the group 5A. In that, nitrogen will have -3 charge, and the rest of them are all variable. Group 6A, oxygen, sulfur, and selenium will have -2 charge. The rest are variable. Group 7A, all of them will have -1 charge, and group 8A, they do not ionize. Now, there's also, by default, the transition elements, which are the D block elements, okay? These D block elements, generally, they will have +2 charges. But then again, there is going to be variable charges as well. So you have to check the table for the variable valence states. Now let's look at the monoatomic anions. The monoatomic anions, like if it is just fluorine, chlorine, bromine, iodine, oxygen, sulfur, phosphorus, and nitrogen, then how do we write their formula and their names? So the name, as you've seen, that all of them are ending in just "ide." Their names are ending in "ide." So fluorine is fluoride. And what does the formula look like? It's just F with 1 negative charge, because fluorine is in group 7A. Chlorine, similarly, group 7A, 1 negative charge. Bromine, group 7A, 1 negative charge. Iodine, group 7A, 1 negative charge. And as you've seen that, they're chlor and ide, brome and ide, iode and ide. So all of them that are ending in ide. Now look at oxygen. Oxygen is in group 6A. Okay, oxygen is in group 6A. That means the charge is going to be 2 negative. Okay, so you can write it like this, or you can also write it like this, 2 minus, or you will also seen it as -2. All of them are correct. Okay, so ox, ide. Okay, similarly, sulf for sulfur, and ide if sulfur is just by itself. And since sulfur is in group 6A, the charge on sulfur is S-2 or S2 minus. Okay, phosp is phosphorus. Okay, and ide is just phosphorus by itself. Phosphorus is in group 5A, so the charge is -3, and you can also write it as phosphorus -3 or phosphorus 3 minus. Okay, similarly, nitrogen, nitride, IDE, and that is nitrogen, and nitrogen is in group 5A, so the charge is -3, and we can write as it N -3. Okay, so these are the monoatomic. When we say mono, means that these elements are just by themselves. When they attach to a metal, then that's what it means. Okay, so their names are going to end in ide. Okay, then comes the polyatomic ions. Now, several non-metals, they combine together and then they form like a stable anions and, few cations. So those are called polyatomic ion. Polyatomic means two or more atoms, and it could be different kind of atoms. Okay, so for example here, nitrogen, generally these are the ones, let's say, they're considered oxidation states because they're mostly combined with oxygens. Okay, different number of oxygens. So if they depends, every atom has a capacity to bond with a certain number of oxygen atoms. So that capacity, that capability is there. So nitrogen has a capability of connecting with two, let me use a different color now, of connecting with two nitrogens, and it can have one negative charge, or it can combine with three nitrogens and then it can retain one negative charge. So in both the cases, there is one negative charge, but you see the oxidation states are different. Oxidation state means when it combines with oxygen. So ite is a lower oxidation state where nitrogen is combining with only two oxygens, and 8 is a higher oxidation state with respect to nitrogen. Okay, and in that case, nitrogen, the maximum capability, the highest oxidation state or the maximum capability of nitrogen to combine with oxygen is 3. And so that is why it's ending in 8. Okay, next is look at sulfur. Now sulfur has also the capability to connect with or to bond with oxygen atoms and different number of oxygen atoms. So sulfite and sulfate. So sulfite is SO3 and 2 negative charges. Okay, and sulfate is SO4 and 2 negative charges. So it's not about the charges. Ite relates to lower oxidation state and 8 relates to higher oxidation state with respect to that particular element. Okay, so sulfur, higher oxidation state, sulfate. Sulfite, lower oxidation state is SO3. Okay, phosphite, similarly, ite and 8. That means phosphorus has a capability of combining with more than, one phosphorus, oxygens. So phosphorus, when it combines with three oxygens, it retains three negative charges, and that is phosphite, PO3 with three negative charges. Phosphate, phosphorus can also combine with four oxygen atoms, and it can still retain three negative charges, and that name now is phosphate. So these are two different species. They are totally different. Their arrangement, the way they are arranged, all that is different. So their properties are different. Okay, now carbonate. Carbon, the maximum carbon can connect with oxygen is 3 oxygens. So it does not combine with 2 oxygens and with the charge, I mean with the holding a charge. So carbonate. So the highest oxidation state of carbon with oxygen is with 3 oxygens, and it retains the 2 negative charges. Okay, so where are these charges coming from and all that comes through the Lewis structures, and we can go into more details in higher chapter in other courses or higher courses. But anyway, so for here, just suffice to remember that don't get confused that anytime there's going to be 8, that means it's going to be 4 oxygen atoms only. No, it is specific to what the atom is that the oxygens are combining with. So sulfur will combine with 3 oxygens, and sulfur can also combine with 4 oxygens. So 3 oxygens will give the name ite, and 4 oxygens is going to give the name 8. Phosphite similarly has 4 and 3 capability combining with oxygens. 3 oxygens, ite, 4 oxygens, 8. Carbonate does not have any lower state with oxygen. It only has one state, and that's the maximum state is with 3 oxygens, and so 2 negative charge. Now this is one thing. Next is chlorine. Now here's the thing. Chemistry has evolved not in a very linear historical fashion. It is if things have been discovered at different points of time. So initially we discovered chlorate and chloride, and I was like, fine. Chlorate is ClO3 1 negative, and that's fine. And then chlorite is ClO2 1 negative. Lower oxidation state, ite. Higher oxidation state, 8. But as the science progresses, the chemistry, new and new discoveries came to say, wait a minute, chlorine also has the capability of combining with 4 oxygens, and it can retain 1 negative charge. So now that is even higher than chlorate. Now they can't change the names, right? So they say, okay, fine, we will have to, this is the highest oxidation state. So that is going to be perchlorate. 8 is a higher oxidation state anyways, but per is the highest oxidation state. So chlorine has a capability of combining with 4 oxygens, 3 oxygens, 2 oxygens, right? And it can also combine with just 1 oxygen. So this one was also discovered, so now they said, okay, it is a lower oxidation state, but lower than the lowest, like the lowest oxidation state, hypochlorite, okay, in this case. So this is how you name them. And again, all this is relevant to every single atom. Okay, so with time and practice, you kind of get a hang of it, and you kind of remember them. The more you write, the more you practice, you can get it. Okay, now comes another thing. Fine, we understand carbonate, sulfate, sulfide, phosphide. We understand all that lower and higher oxidation state. But what happens if you add hydrogen in front of sulfate, phosphate? So here becomes bicarbonate. And notice the charge. Carbonate has 2 negative charges. Look at this carbonate here. This is 2 negative charges, CO3 minus 2. Okay, so carbonate, 2 negative charges, but the moment you add hydrogen to it, that 1 charge gets neutralized, because hydrogen, it's actually a proton, okay, H plus charge. So it is now bicarbonate. Okay, 1 negative charge. Now let's look at bisulfate. So sulfate has 2 negative charges, but one of the charges gets, neutralized with the hydrogen. So this is the bisulfate. Now comes the phosphate, PO4. PO4 has 3 negative charges. So, but one of the charges gets neutralized, and you are only left with 2 negative charges. So that's the biphosphate. So it's also called hydrogen phosphate, hydrogen sulfate, hydrogen carbonate. So those things, okay? Now comes the hydroxide. Now this is different. Now here, you notice the replacement of hydrogen. Hydroxide, okay, don't get confused. Hydroxide, it means that maybe in your mind, you may think hydrogen should come first and oxygen comes later. But all these names came in different, times. And some of the substances already got their names and like more commonly used and so forth. So later on, they decided to do the IUPAC naming system, and in which they try to clean and purify. But certain things, just they had their names. That's it. So this is hydroxide. So oxygen is written first, hydrogen is written in the end. So just pay attention to this one. Hydroxide and then the bicarbonates. So bicarbonates does not mean 2 hydrogens or 2 carbonates. It doesn't mean that. It's just the placement of hydrogen is in front, here, and here hydrogen is at the back. So that's one point to note. Okay, next is other ones. We just now looked at the naming with respect to the, these were all non-metals. These are all non-metals. Okay, all the non-metals. And so basically these are all monoatomic anions. These are again non-metals: fluorine, chlorine, bromine, iodine, oxygen, sulfur, phosphorus, and nitrogen. These are all non-metals. And I'm going to put it here. These are non-metals, and these non-metals have, let's write down just 1 minute. Okay, so all right. Okay, so here we have these non-metals. These non-metals can react to themselves and have these ions, which makes the polyatomic ions. But some of the metals also, form, anions. So here we have chromate. So chromate is CrO4 and 2 negative. So okay, so C is chromate. CrO4, 2 negative. Okay, so that's chromate. But dichromate is Cr2O7 and 2 negative. Okay, so dichromate here, di means two chromates. So just by itself, chromium It's coming from chromium. 8 is obviously, so that's chromium. Okay, chromium. And next is the permanganate. Now that is coming from manganese. So this is MnO4 1 negative. Okay, permanganate. Just like perchlorate, same thing, permanganate. Okay, then there are some special ones like cyanide. Cyanide, so some of them you just have to commit to memory. Cyanide is Cn-1. Then comes the thiocyanate. Thiocyanate, now this one is thio. Thio stands for sulfur, sulfur based. So this one is SCN1 negative. Okay, thiocyanate is 1 negative. Then comes the acetate. Now acetate is CH3COO 1 negative. And this is also written as C2H3O2 1 negative. Okay, so this is the other way of writing it. So then comes the ammonium, NH4 and +1. So this is the only one ammonium in your list so far, which has the positive. This is a positive anion. So pay attention to that. Ammonium is NH+4. Okay, so pay attention to this piece right here. So it's the only positive one. Okay, so ammonium. Okay, that's one thing. Now let's look at the cations with multiple charges. Now these are the metals. Generally they are in the transition elements and the post-transition elements. Okay, so the ferrous transition, the D block element. Okay, so let's see. Let me do this in this color. Okay, ferrous. Now here, when this is also the oxidation state, but we can let's call it valence state. Valence state is like, the charges, the less number of charges, us, higher number of charges, ik. Okay, so valence, the lower charges, us, higher charges, is. So this is us and ik. So us is Fe +2 and ik is Fe +3. Okay, Fe +2 and Fe +3. So Fe +2 in Roman numerals. So this is how we write them in the Roman numerals. Roman numerals 2 and then Roman numeral 3. So that's the Fe +2 and Fe +3. Okay, so this is also called ferrous and ferric. Lower oxidation state for cobaltous, which is 2. So this is cobalt and +2. And cobaltic, higher oxidation state, cobaltic is +3. Now again, do not confuse that every time us is going to be +2 and ik is going to be +3. No, it is always specific to what the element is. What element are we talking about? We're talking in this case of iron. Iron has +2 and +3, cobalt +2 and +3, but copper on the other hand has +1 and +2. So I'll put this in a different color here. Cuprous is +1 and cupric is +2. Cupric is +2 oxidation state. So copper in +1 state is us, and copper in +2. That's the highest, charge that copper can have. And again, all that relates to electronic configuration. Okay, and so we have here copper with +2 and copper with +3 like the valence charges. Then comes the stannous, and again here, if you look at stannous, this is tin. Okay, commonly, commonly it is known tin, but the Latin name is stannous. So stannous. Now here it's different. Look at this. So stannous and stannic. The lower oxidation state is +2. The higher oxidation state is +4. So Sn +2 and Sn +4. So higher, the valence state +4. And it's fine to say oxidation state, but I don't want to confuse you because there's no oxygen here. But that's another way of saying it. But so lower valence state, or the lower charge, +2 in tin, and higher charge is plus 4. Same is the case with lead. So if you look at lead again, with respect to lead alone, there is plus 2 and plus 4. And that means that the lead, the symbol is Pb, okay? The lower oxidation state is plus 2 state, and the higher oxidation state is plus 4 state, okay? Plumbic. And we write it in the Roman numerals as is seen on the left right-hand side. Then comes the chromium. Chromium is, let's see, another color, chromium. So here is chromium, and this is chromium. Chromium, chromiumus, I believe. Chromium, so I have to fix this one here. Anyway, so this is going to be plus 2 for chromium, and this is plus 3. Okay, so that's the thing with these charges. And so chromic, so this should be us, chromus, and chromis, or chrome. Okay, now we have these, so two ways you can write these elements, which are the transition and the post-transition elements, and not all of them, but these are this, and there are a few more. They exist as in variable valence states, and these variable valence states can be written in two ways, either in the us and the ik format, or in the Roman numeral format, as you can see on the side, right hand side. Now let's just go quick review on the Roman numeral. So how do you write the Roman numerals as how do you write the Roman numerals? So 1 is written like this, 2 is this, 3 is this, 4 is this way, 5 is like a V, 6 is like this, 7 is this, 8 is 1, 2, 3, 9 is this, and 10 is this X. 11 is X1, and 12 is X11, and 13 is X111, and 14 is X1V, and 15 is XV. Okay, and so forth. So this is how you write the Roman numeral. So just, review on that. Now we are going to look at the numerical prefixes for the compounds that are hydrates and the binary covalent compounds. So mono stands for 1, di stands for 2, tri stands for 3, tetra stands for 4, penta stands for 5, hexa stands for 6, hepta is 7, octa 8, nona 9, and deca 10. And we can go further, but that's kind of like for this course, it suffices to here. So this also means, like when we say pentahydrate, means five molecules of water. Okay, that is pentahydrate. Now, on the other hand, if we say hexachloride, this means 6 chlorine atoms. Okay, so we will look into it further. Let's look at the acids now. Now, the acids are two types. One is the binary acid, and the other is oxo acids, the ones that contain oxo anions, in other words, ones which contain oxygen. So the ones that are without oxygen, how do you name them? So you start their names with hydro, and then you look at the non-metal, and the name of the non-metal is going to end in ik. So for example, now here's something very important to pay attention to. Pay attention to this and this. This means in the aqueous medium, AQUEOS, aqueous medium. This also means with respect to water, okay? Water, when there is water. So when HCl is bubbled in a gaseous form into water, it forms hydrochloric acid. And so what is the name? Now the name becomes hydrochlor, and it's going to end in ik and acid. That's the name. Next is the hydrobromic acid. Okay, so an important piece right here is that if that you see aqueous written, then only then it is going to be an acid, otherwise not. Okay, otherwise not. Otherwise it's a gas. and we will look into it in a minute. Then comes the oxo acids. Oxo acids are the ones that contain oxygen. Okay, so they are polyatomic ions. Okay, now with the polyatomic ions. So again, the polyatomic ions, recognize that SO3 lower oxidation state and SO4 higher oxidation state. In other words, SO3 lower polyatomic ion, SO4 a higher polyatomic ion as far as the number of oxygens are concerned. So lower oxygens, number of oxygens, sulfite, SO3 with two negative charges. Sulfite becomes, ite becomes us, OUS, us. Ite changes to us. Higher number of oxygens, 8, with respect to sulfur in this case. The name changes from 8 to ic. So you see H2SO3 versus H2SO4. H2SO3, sulfurous acid, and H2SO4, sulfuric acid. So yeah, they are both ending in acid. The only thing that changed is with respect to the polyatomic ion, their names change from ite to us and ate to ic. Now comes the oxo anions, which have the prefixes. For example, perchlorate, perchlorate. So yes, the per is retained, per doesn't change, per is remaining the same. The only thing that changes, the 8 higher oxidation state becomes ic, and then you put the name and end it with acid. All right, so this is how you call these acids. Now, we already talked about the group numbers, and now let's look at the nomenclature and some of the examples. So all that we learned. Now, you are welcome to, if you are lost, you're welcome to, obviously stop the video and then go back and look at the tables. My recommendation is that you should make notes in your own handwriting of these tables on a separate sheet of paper or index cards, because then when you're writing, you kind of remember. It's too many things to remember in chemistry. So you have to do some, create some, when you write, you learn more that way. Okay. So here's the thing, nomenclature of now potassium iodide. So we're going to look at writing their names, and we're going to look at writing their formulas. Okay. So potassium. Okay. Potassium. Excuse me. Sorry about that. Okay, so here, look at potassium is symbol K. It's in group number 1A, so the charge is going to be +1. Okay, +1 charge. Iodine, iodide, it means that it is just iodine just by itself. Fine, it's coming from group 7A, the charge is -1. So first, always do that. Next is write down there, like this is crisscross. So this number comes and the subscript becomes a subscript of iodine, and this 1 comes here. Now you are not bringing in the negative and the positive charges, you're just bringing the numerical values. So here you are going to write down, the name now is Ki, the formula, sorry, Ki, and the name is potassium iodide. So the name of the metals doesn't change. The name of the metal remains the same. The non-metal, if it is just by itself, it's a monoatomic, non-metal, then it becomes ide. Okay, let's move to the next one now. Magnesium. I'm going to just leave it here. Magnesium. So here is your magnesium, Mg. Magnesium belongs to group 2A, charges +2. All right. And nitrogen, group 5A, charges -3. Remember, we covered these over here in this table. So group 5A, nitrogen, charges -3. Okay. Now, next is, all you're doing is crisscrossing, which means that you are bringing in this 3 over here as a subscript for magnesium, and this 2 goes as a subscript for nitrogen. So, and again, this comes with through practice. So here is your Mg 3 and 2. Okay, Mg3 and 2. This means that there are 3 magnesiums and 2 nitrogen atoms in a molecule of magnesium nitride. And again, ide means it's just nitrogen just by itself as a polyatom, as a no, as a non-metal. Okay. Next comes calcium. Now let's look at calcium oxide. Calcium, again, very important for you guys to recognize the names, names and the symbols, right? The names, associate the names and the symbols. So here we have calcium. Okay, calcium is Ca, right? And the charge, it is in group 2A, so the charge is +2. Oxygen is in group 6A, the charge is -2. Okay, so group 6A, charge -2. This number comes here, and this number goes, this number goes at the base of subscript for oxygen, and this number subscript for calcium. So what happens here? Now we have, interestingly, calcium. So first now write down 2, and oxygen is 2. But you simplify, and in a simpler version, it is CaO. Okay? You see that the charges, they cancel each other out as far as they're same, because they're same. And you always write down the simple whole number ratio. Simple whole number. If you can simplify it, then you should put this in the simpler form. So that is why the real formula of calcium oxide is CaO. Okay, next is ferrous sulfide. So now it tells you ferrous, lower oxidation state, lower oxidation state. Sulfide, it is just sulfur by itself. So here is your iron. And again, with practice, you can memorize this, but for now, we are looking at ferrous and ferric. So which table are we looking at? We're looking at this cations with multiple charges. And there you see us with regards to iron. It's us is Fe +2 and Ik is +3. Okay, so here you're going to write down the ferrous, Fe +2. And here is your sulfur, group 6A. Group 6A means that it has -2 charge. Okay, so group 6A is -2 charge, and for sulfur and iron, us is +2. So now you crisscross. So this 2 comes here, and this 2 goes there. And, same story as above, we will have iron and sulfur. And so this, again, you need to simplify, and it becomes FeS. You see the interesting part? Iron has +2 charge, sulfur has -2 charge, but the formula is just showing FeS, So because those charges cancel out, and you make it into a simple whole number. So this, and the other name of this is going to be iron 2 sulfide. That's the next name. All right. Next is, you're going to look at, the next one is the ferric sulfide now. Ik, higher oxidation state. Sulfide, it is just a sulfur by itself. So here is your iron +3, and here's your sulfur -2. Sulfur, group 6A, charge -2. Ferric, from the table, it's the +3 charge. So 3 comes here and 2 comes here. So now you have Fe, so this becomes Fe2S3. And since 2 and 3 cannot further be simplified, so this is just as it is. So this name is just going to be Fe2, so formula is Fe2S3. And what do you write? Iron 3 sulfide. Iron 3 sulfide. All right, so this is how. Then comes tin 2 oxide. So always very important. By this time you should, memorize the names and the symbols of the elements. So here you have tin. Tin is Sn. And when it is saying in the parenthesis 2, that means it is tin +2. Okay, so tin is +2 oxidation state. I mean, the way the charge is the oxidation, and then oxygen charge is +2. Sorry, oxygen oxide. It means only oxygen. The charge is -2. You see that? So now you bring in same story. You're going to bring in 2 subscript here and this 2 as a subscript there. So what will you get here? You're getting SN2O2 and simplify again. So this becomes SNO. SNO. Okay. So this also, the name is stannous. STANNOUS. Stannous oxide. Stannous oxide. Okay, because it's a lower oxidation state. We also know that tin exists in a higher oxidation state, which is 4. So in that case, it is SN +4 and oxygen -2. And same thing, crisscross, bring this over here, and this 4 goes, base of oxygen. Let me just write this properly. So this 4 comes here, and this comes here. Okay, so they're just switching places. So now you will have SN2O4. And when this one can be simplified. So this becomes SNO2, right? And SNO2 means that it is stannic, higher oxidation state, oxide. Okay, now this was, with the simple monoatomic, anions and variable valence state. Now let's look at the polyatomic ions. Sodium is in group 1A. The formula of the symbol of sodium is Na. The charge is +1. Hydroxide, polyatomic ion, the charge is -1. Okay, now again, here, this 1 goes here, and this 1 goes here. So this gives you NaOH. Okay, so all of this is 1. For 1, we don't write. Okay, it kind of means, it's 1 because we don't write, for 1. So this is sodium hydroxide, and sodium is in group 1A, so it's not a variable valence state also. Next comes the aluminum sulfate. Okay, aluminum sulfate. Aluminum is Al. Okay, and sulfate is SO4. Okay, the charge on aluminum group 3A +3 charge, and sulfate is -2. Okay, now we are going to bring in this 2 comes here, and this 3 is going to, sorry about that. Let's just do it. This is aluminum group 3A, charge is +3. Sulfate, polyatomic ion, it has a standard charge. Those things don't change. So this 2 comes here to the subscript of aluminum, and this 3 comes here, subscript of sulfate. Let me just put this one first. So here is this 3 is going to come here, and this 2 comes here. Okay, so they cross, or they change, they switch places. So here we have aluminum. Now here's the thing, aluminum is +3, so more than 1. So that means sulfate is going to be put in the parentheses. So here you have aluminum 2 parentheses sulfate 3 whole thrice. So because +3 is more than 1, right? And sulfate is -2. So you need to put the polyatomic ion in the parentheses, okay? Because it's a SO4, otherwise it becomes SO43. That doesn't make sense. So this means there are, for every 2 atoms of aluminum, there are 3 polyatomic ions of sulfate. Okay, so this is how. So this is just the name, aluminum sulfate, aluminum metal sulfate, polyatomic ions. So here's the easy part. The name of the polyatomic ions don't change. So they remain the same. So now look at this. Phosphate, PO4, the charge is -3. Okay, and zinc is a transition element. right? D block. And so by default, all D block elements by default will have +2, but keep this in mind, then there are exceptions to this rule also. So there are also elements that can form, different, they can exist in different, valence state, in different charges, but, for the most part, it's +2. Okay, so, and then, we can do the electronic configuration to see if it really is +2 or what. So that's one thing. Okay, now here's the thing, zinc and phosphate. So this 2 comes here and outside of phosphate in the parenthesis. And the 3 goes here at the base of zinc. So now what kind of formula do you get? You get Zn3 parenthesis PO4 parenthesis goes twice. Zn3 PO4 whole twice. So that's zinc phosphate. Okay, so 3 and 2 cannot further be simplified. Okay, let's look at copper nitrate. Copper 1 nitrate. Now here it's copper. 1 means +1 charge. Nitrate is -1 charge. So now same thing. This 1 comes outside of nitrate. But anytime you're bringing in 1, it doesn't, it doesn't change anything. It remains the same. So here we have here copper CuNO3. So anytime you're bringing 1, you don't do anything to the polyatomic ion. I mean, you don't put it in the parenthesis. Now comes copper 2 nitrate. Now this is different. Copper +2 charge and nitrate is -1 charge. So what do we do here? We are going to bring 2 here and this 1 goes here, but when it comes to 1, we do not write. So in that case, what do you get? So you get Cu for 1 that we brought down from nitrate, we don't write that, but we brought 2 down from copper, and this is the nitrate in the parenthesis we had to put because it's 2 is more than 1. So this is the formula for copper 2 nitrate. So this name also is cupric, higher oxidation state, cupric nitrate. And the top one which we did here was cuprous nitrate. Okay, cuprous nitrate and cupric nitrate. Okay, next is look at the ammonium chloride. Ammonium chloride is ammonium NH4 with +1 charge, and chloride, ide means it's just chlorine by itself with -1 charge. Okay, so when you bring these charges down, you don't write 1, but this means that for every 1 ammonium, you need 1 chloride. So the formula is NH4 because that's ammonium by itself, and chlorine is Cl. And so when positive and negative charges cancel out, you get this NH4Cl. Next, look at ammonium carbonate. So here is your ammonium NH4 with +1 charge and carbonate 8, and that's carbon. So carbon, oxygen, 3 oxygens, 2 negative charges. Okay, so now we are going to take this 1 comes here and this 2 goes outside of ammonium because 2, 2 is more than 1. So how do you write this? This is NH4CO3, but we brought 2 down, right? So here. So this means that for every 1 carbonate polyatomic ion, you need 2 ammoniums to neutralize it. And it makes sense. Carbonate, 2 negative charges, ammoniums, 1 negative charge. That's why you need 2 ammoniums to neutralize those 2 negative charges. Okay, so the molecules by themselves don't have any charge. It's all neutralized. Next comes potassium dichromate. Now here's an important part, dichromate. This is already polyatomic ion. This is the name of the polyatomic ion. It is Cr2O7 -2. Okay, so this is already there. Dichromate, that's the formula. And then potassium group 1A +1 charge. Okay, so same thing. This negative charge, this positive comes here, and this negative, this 2 comes here. So what do you get here? Potassium dichromate is K2CR2O7. All right. Next is the hydrates. Hydrates. Now look at copper 2 sulfate. Copper plus 2 charge, sulfate minus 2 charge. So, and then penta means 5, and then hydrate is water. Okay, so how do you write this now? You're going to write down this CuSO4. Remember, those two positive and negative cancel out. Dot 5H2O. That's for the hydrate. Hydrate stands for water. I'm going to just put this here. This is hydrate, means water molecule. So there are 5 water molecules attached to one molecule of copper 2 sulfate, cupric sulfate. Okay, but commonly it's copper sulfate. Okay, next is magnesium sulfate, heptahydrate. So again, hydrate stands for water. Hepta is number 7. Sulfate is SO4, 2 negative, and magnesium is in group 2A, so it has plus 2 charge. So when these are combined together, they cancel each other. It becomes MgSO4 dot 7H2O. So that is the formula of this magnesium sulfate heptahydrate. Next, look at the acids. Acids, again, perchloric acid is HClO4, and this we already covered it. So it's coming for perchlorate. So all acids are going to end in with the word acid. Now, perchloric acid, its name is retained, like perchlorate, 8 becomes ic. So this is coming from perchlorate. So 8 becomes ic, okay? Similarly, chloric acid. Chloric acid is again ic. That means it was 8. So this is HClO3. Okay? So that's the difference between perchloric and chloric. Both of them have, chlorines. Oh, wait, perchlorate. Yeah, that is perchlorate, exactly. Okay. Next comes the phosphorus acid and phosphoric acid. Phosphorus, lower oxidation state. Phosphoric, higher oxidation state. H2SO3 versus H2, this is phosphorus, my mistake, I'm sorry here. So this is, let's do this again, phosphorus, H3PO3, and this is H3PO4. So ic, higher oxidation state, and us, lower oxidation state with respect to, in this case, this is the phosphorus-based acid. Okay, hydrobromic. Now here's something else. Now this is not, hydrobromic acid. Hydrobromic acid is HBr, but it's very important that you write AQ over there in the parenthesis. Then H, hydroiodic acid, hydrogen, iodine. So remember iodic, and then bromic. So this is non-oxygen containing these two. So make sure that you put the aqueous here. I mean, all acids you need to put aqueous by default. All of them will have aqueous because all of them in water. Okay, they're all water-based acids. Okay, so these are inorganic acids. Next comes the covalent compounds. Now for the covalent compounds, we use the suffix, the prefix, the mono, di, tri, tetra. So these are reserved only for the covalent compound. So do not use mono, di, tri, tetra type of terminology for ionic compounds. The mono, di, tri, tetra is reserved only for covalent compounds. And what are covalent compounds? Covalent compounds are formed when non-metals, they bond with each other. Okay, and so by this time you should know what the non-metals are. Non-metals are on the right-hand side of the periodic table, the ones that are on the top right-hand side, and of course the halogens. Okay, All right, and so now we have carbon monoxide. So here is your carbon. Mono means one, oxygen, oxide, ide means that it is just one oxygen, like one kind of atom. So one oxygen, oxide. So this is carbon monoxide. But when we say carbon dioxide, means we are saying two atoms of oxygen. So this mono di, this applies to, what it is connecting with, what the next element is. Okay, so sulfur dioxide. So here is your sulfur. Dioxide means two oxygens. Okay, so here it is one oxygen. Here there's just two oxygens. Sulfur trioxide is three oxygens. Okay, so that's a ditto sign. And then comes carbon tetrachloride. So here is your carbon. Tetra means four chlorines. Okay, so four chlorines. All right, then comes dinitrogen pentaoxide. Dinitrogen means two nitrogens, pentaoxide means five oxygens. Okay, dihydrogen sulfide is H2S. Hydrogen chloride. Oh, this shouldn't be, sorry, I made this here. This shouldn't be oxide here, dinitrogen pentaoxide. Yeah. So here is your hydrogen chloride. And this is a gas. It's very important. This guy is also a gas. Okay. Hydrogen bromide, HBr, and gas. So when hydrogen bromide means it's in a gaseous state. But when we say hydrobromic acid, that means it's in the aqueous state. Okay, so this finishes this concept of nomenclature here, and we are going to look at the nomenclature that relates to organic compounds. That's a separate, method. So we will do that in the next video, but I hope that was easy and helpful. Thank you.